and I'm here with Frank Gardella, and we will be your presenters for this afternoon. Okay, so my first question to you is, what is mathematics? Before we start talking about algebraic thinking,
the broadcast is now starting. All attendees are in listen-only mode.
It's been defined as mathematics is a science. It is a science, and it is an exact science. It is exact. And it's the science of patterns, numbers, shapes, and relationships. And I think the important part is what we understand here is that math is the science of patterns. Math is always it's also a language. It's a language of symbols. I know when I talk to my friends who teach science, I always say that math is the queen of all sciences because you cannot do the chemistry, the physics, the biology without mathematics. So it is the language. It's the language that helps us to understand the sciences and the world around us in economics, in history, in social studies. It is a language. So that's an important part that people should understand, that mathematics is a language. So what we're here this afternoon is to talk about what is algebraic thinking and or reasoning. So we talk about algebra and we say that algebra is a generalization of arithmetic. So algebraic thinking is that generalization of these operations to look at the patterns, to generalize, to develop a sense of what's going on. So it's a thinking process, it's a formation process of looking at what I see and what I can generalize about what I'm seeing. So it's a generalization. It uses the symbols, which is the language of mathematics. So let's talk about what are the components of algebraic thinking. It's the problem-solving skills. It's that ability to reason through problems and look at how do I go from step 1 to step 2? What is the process that I need to go? It's representing these skills in a symbolic language. And of course we hear about habits of mind. Well, how do we get students to develop this as being a process that is internalizing to them? There are 16 habits of mind, which some of them are called a fluency, a persistence. Well, how does that help us in mathematics? Well, when we look at the habits of mind, it's looking at finding a pattern, making lists and tables in mathematics, coming up with an equation. It's looking for a structure and not just memorization. We're looking to have our students not memorize things but understand the structure, become that habit of mind. So what are the elements of algebraic thinking? Algebraic thinking is that ability to look at a problem, describe the patterns, the relationships, do it through the problem-solving skills that we have, come up with a diagram, come up with a table, but most of all, come up with the symbols, the symbolic, looking for the relationships between what we are doing, looking at graphs, all of what is leading to what we're going to talk about this afternoon, and looking at building relationships, building these patterns, and coming up with a generalization. Doing it, again, through looking at graphs, tables, and the symbolic notation. Okay. The most important part about any of this is that verbal, that ability to explain what they're doing, that ability to have the students describe everything so that we can understand what their conceptual understanding is, and being able to express that notation. I think if you go back to NCTM, one of the standards is communication, and an important part of anything is that ability to communicate what I see, what I'm doing. All of the standardized tests today have these open-ended questions. We're looking for the students to explain, to communicate what they are doing. So what are the outcomes that you want from the algebraic thinking? It's that ability to make connections, that ability to look at the understanding, especially proportionality. Ratio and proportion are what they call the capstone of elementary and the beginning part of looking at what they're doing in advanced math, to look at these problems in different ways, to do them through the rule of numerical, graphical, and analytical. So it's the rule of three, which now became the rule of four: numerical, graphical, analytical, and communication, that ability to communicate, to understand what you are, what these quantities represent, to look at that, and to have them be able to see things that are linear and nonlinear.
Okay, so from the last time, we're going to go through a number puzzle, and we're going to go through the number puzzle in two or three times, looking at the attributes of what Maria was just talking about and how we can gather this from a simple thing like a little number puzzle of finding the right number. So here's what we'd like you to do. And this is the number puzzle from last time for the upper grades. You pick a whole number from 2 to 5. Okay? All right. The next thing we want you to do is multiply it by 2. And that'll come up on the screen pretty shortly. There it is. Okay, so we want you to multiply it by 2. Then we want you to add 3. Next step would be add 3. Then the next step, step D, will be multiply by 2 again. I think our computer's been playing in the snow. There it is. Okay? And D is an important step, and I just want to mention that to you. Okay? Then we would subtract 6. We just canceled something, and here we are.
Go.
Okay, we're going to go next step.
I don't know why it's
Would be subtract 6 and then divide by 4. Okay? And the question becomes, what number do you have? Is it the one you started with? Now, if it's not the one you started with, then I'll just say you should check your arithmetic, because it was the number you started with. But what we're going to do now is we're going to do something a little differently. We're going to start with the same number puzzle, except this time, as I said, we're going to stop at instruction D. So here we have the 4 instructions. So you're going to pick a number. What I'd like you to do is try this right now. Pick a number, a whole number, from 2 to 5. Okay? Write it down. Then from that, the answer to step A, multiply it by 2. And from the answer to step B, add 3. And for the answer from step C, multiply it by 2. And that's step D. Now put a circle around the number you started with. Whatever number you started with, put a circle around it. And then put a square around the total that you now have. After step D, you'll have a total, and we want to talk about that total. And I just revised it right here, or gave you an example, I guess I should say. For example, if I chose 5, I put a circle around 5, I would multiply it by 2, add 3, multiply by 2. After I did all this, I would have a total of 26. So I put a circle around 5, my number, and put a square around 26, my total. And now, if you've heard those terms, number and total, several times, you'll now see why we are talking about number and total. Here what we've done is, we've done a table of values showing all of the totals for the numbers 2 to 5. The left-hand side of the table of values are the numbers you could have chosen, 2, 3, 4, and 5. And the right-hand side is the total. These are the numbers that you would get after step D. If you went to step F, you would get back to your number. But if you stopped at step D, this is what you would have in terms of your total. So if you chose 2, you get 14. If you chose 3, you get 18. 4 gives you 22. 5 gives you 26. And what patterns do you notice on that table? Here are some of them. And here is where you start to look at individual arithmetic things and possibly start talking about more generalized ideas. So the first one is, as the number increases by 1, the total increases by 4. Another idea is, as the number decreases by 1, the total decreases by 4. So when you look at both of those, you can generalize that, and you can say, as the number changes by 1, the total changes by 4. And what we should have added there was the total changes by 4 in the same direction. And so in the upper grades, this then leads to a nice discussion of ratio and proportion, or at least ratio.
And in the lower grades, if you're doing this number puzzle, what you can ask them is to generalize what are the arithmetic operations. What are the arithmetic operations that you notice? Because when you multiply and divide, that's undoing addition and subtraction. So when you look at this, it's a way of saying that here these number puzzles work for both the lower grades and for the upper grades.
Here's another additional type of thing. As the number increases by 2, the total increases by 8. As the number decreases by 2, the total decreases by 8. So again, we can say, as the number changes, which is generalization, as the small generalization, but still for some kids a generalization, as the number changes by 2, the total changes by 8 in the same direction. So now we are beginning to look at proportions as well as ratios, just using a simple number puzzle.
So in talking about these changes, and you're looking at and you're saying, well, here's proportional reasoning. Proportional reasoning is that capstone of the elementary grades of arithmetic, and it's the cornerstone for everything that's going to follow. Much of the research shows that students need a good handle on what is ratio and proportion, that proportional reasoning, to be able to really succeed in the advanced courses. So this is the research by Dick Lesh and his colleagues, and it was from 1988, but it's still ingrained in us that proportional reasoning is a big part of what we need our students to be able to see. The number puzzle was a nice way of looking at the totals and coming up with that concept that our change was for every 1, it changed 4. There's the ratio. For every 2, it changed 8. There's the ratio. And what does that mean? So if you go back and you look at the standards, it's telling us that standards should use ratios and rates to solve real-world and mathematical problems, doing it through tables, through number lines, through diagrams and equations. Well, we just showed you a table way of doing it, and we showed you a way of coming up with a number sentence to be able to do this. So you're looking at making these tables and relating them to whole numbers. Being able to find, you can continue that table and ask the students, if I wanted to find out for 6, we went from 2 to 5. Now what would it be for 6? Using it as the missing value. Do they really understand that if I increase by 1, I'm going to increase by 4? So being able to make comparisons too of what's going on here. So to identify that constant of proportionality, well, we just define that constant of proportionality by looking at the representation. So these are all things that are in the standards that are important for the students to have that proportional reasoning. Algebraic thinking, which is leading to proportional reasoning. Here's a very simple problem for the lower grades. It's called the hand of the giant. During the night, A giant entered our classroom, and while stumbling in the dark for the light switch, the giant left a large smudge. So you're looking at this handprint, and so now you want to know, and you're looking at it and you're saying, okay, if I want to find out the height of the giant, so I've got this handprint, how can I find out the height of the giant based on what I have at hand? So when you're looking at it, you say, well, I have a hand, the giant has a hand. Looking at the number puzzle, can I find out what the rate of change is here, what that ratio is? So here would be a possible solution. Here here's the giant's hand. You make a copy of the giant's hand. Here are the children's hand, and you're looking at 4 children's hands make up 1 giant's hand. So again, for every time I'm going to make a change, 1 giant hand will give me a change of 4 children's hands. So here you're saying that the change here is 4 to 1, just as what we found in our number puzzle. The rate of change was 4 to 1. So these concepts, whether it's a diagram or a table, can be done as early as this could be even done in the 2nd grade.
So now we've looked at the arithmetic or the arithmetic model for our number puzzle, namely the table of values. Now we're going to look at a picture, a table of values. That is a graph. So on the next slide is the graph. Now, here's the difference here. The axes of the graph are going to be number and total. Why not X and Y? The students are discussing the idea of number and total. Why insert something, X and Y, that you would have to explain? Let them go with what they are saying, naming number and total. And as I put down at the bottom of the slide, later for X and Y. And I think this is something in the teaching of algebra in the before an Algebra 1 course that we have to be very, very much aware of, that we are not basically enslaved by this concept of X and Y, that a lot of algebraic concepts can be developed by using the names of the things, for in this case, number and total, so that children don't have to relate, in a sense, number to X and then X to whatever is happening. It's just number to whatever is happening. And that direct correlation is really helpful in getting them to move ahead. Okay, so here's our graph paper. Notice that there are 2 axes. The horizontal axis down at the bottom is the number, and the vertical axis is the total. Now, one other thing I want you to note, and this is something Marie and I use with high school people also. If you'll notice that the graph paper is already numbered. And the reason for this is one of the greatest wastes of time in the teaching of algebra is having kids number their own graph paper. And boy, I think anybody who's been in a classroom more than 10 minutes with a group of kids numbering their graph paper, they know that they can really make a full period out of it. So what we've done here is, and we use this in initial teaching, is the idea that the graph paper is numbered. Now, if by the end of the year for some test you need to have them number their own graph paper, there's ample time for you to take this as a model, this model that they've seen, and have them replicate it on their own. Now here's our table of values from before. 214, 318, 422, 526. We're keeping it as a table of values. We're not putting it in ordered pairs, and that depends upon how well your students adjust to changes. For example, some kids can look at this and say, okay, 24, 318, 422, 526. You could write them as pairs. They would remember that the first number was the number and the second entry was the total. Some children will not be able to do that. So as a result, you will keep the table of values in front of them for the entire time that you're working on these materials. And here are the 4 points when you graph those 4 number pairs. So down towards the middle of the graph on the left, you have 214, which means 2 across on the number and 14 up on the total. The next one is 318. The next one is 422, and the next one is 526. I've made them quite large just so that they would stand out. And when we connect the dots, as you might say, you get a straight line. And I think that is a nice place where you can start talking to kids about the idea of linear relationships. The reason they are called linear relationships is because when you look at their graphs, there's a straight line. Now, one other thing that comes out of this also, and this is an extension off of the main topic, we've asked you to choose a whole number, 2, 3, 4, or 5. What happens in the classroom if you have somebody who decides to pick 3.5 or 3.5? It's a nice teaching opportunity, because now you can say, if someone has chosen as a number 3.5, how can I find out what total they should have gotten? One way would be to give the children a calculator to stay out of the computation. But the other way would be to go across the number axis to halfway between 3 and 4, and then move all the way up, halfway up through the blocks, until you hit the line itself. And if you'll notice, if you do that, if you put your hand on the screen and just kind of, as a geometry teacher I had used to say, choo-choo up the line, you will find that it hits the screen at 20. And that's interesting also, because at 18, at 3, it's 18. At 4, it's 20, 22. And now here we have 3.5, it's 20. Again, the relationship, the balancing of the ratio that we've been talking about. So now we have seen our number puzzle in two ways. We've seen the table of values where the pairs have a common ratio. Later on, I guess we could call that the slope and call it whatever you want. But right now, we're just going to call it a common ratio. And as a graph, we have these pairs that are on the same line. And that's creating the idea that we have a linear relationship, or a relationship in a line. So now what we're going to do is we're going to look at our number puzzle and, in a sense, write it using a formula. And really, in a sense, when you talk about algebraic thinking and what algebraic thinking is all about, pieces of algebra have been in the elementary and middle school curriculum, because as soon as you get into measurement and you start talking to students about formulas, there is a form of algebra. It's an expression, it's a generalization. The area equals the length times the width, where the length and the width are not specified. That's an algebraic representation of area. Now, to do this, we will work with the models that we did in our last webinar in terms of specifying a stick type of as our number, and then little pieces as our ones. And what we will do is we'll go through our number puzzle again up to step D and see what we have. So here we have again, we have the language that we're going to use in our number puzzle. We have the manipulative, the bar, which is going to stand for our number, and then we have the symbol N, which is standing for our number. So the first thing we were going to do was double everything. So we multiply by 2. That means we get 2 bars, and we write that as 2 n's, or 2 n's, or 2 times n. And there are several ways that you can say that. You have to pick up the one that you feel your students will be most comfortable with. Saying 2 n's at this point is somewhat comfortable for kids. The next thing we had to do in the number puzzle was add 3. So if you'll notice the manipulatives for this, or the models, are 2 bars, or 2n, plus 3 ones. And our symbols are 2 n's and 3 ones. And what we have found, and this happened in an algebra class that one of my teachers was doing when I was in East Brunswick, what we found was that the use of the materials in the middle do not really help students not to make the typical mistake of saying that 2n plus 3 is 5n. I hate to say that being recorded, because somebody could take it off the recording and said that Frank said that one time. So this is an idea that why you can't add 2n and 3, because 2n is 2 bars and 3 are 3 ones. They can't be added, they're different things. And the next step was to multiply by 2. And what are we multiplying by 2? We're multiplying our 2 bars by 2 and getting 4 bars, and we're multiplying our two sets of 3 ones together, and we're getting 6 ones. And if you'll notice under the symbols, it comes out to be 4n plus 6. The 4n plus 6 comes from doubling the 2n, or multiplying the 2n, and then multiplying the 3. And if you'll remember, if you were in our webinar last week, we said when you do this, when you take an expression like 2n plus 3 a number of times, in this case 2 times, and you have 4n plus 6, that's an application of the distributive property of multiplication over addition. So in this respect, we've used the distributive property of multiplication over addition in this last step, step D, to get our bar representation and now our symbolic representation of 4n plus 6.
If you look at this, we've gone through the steps where, as algebraic thinking and habits of mind, being able to make the transition from the language to the symbols using whatever tools. The tools we're using here are manipulatives. For the lower grades, if you do not want to get into the symbols, here's the language, here are the manipulatives, and you can see the representation and to ask them to describe it. And if you finish the number puzzle like we did in the beginning, you can go through the steps further with the manipulatives, having them subtract, having them divide, and then seeing that they get back to their original number. So these manipulatives and this type of a problem is not only for the upper grades, it can be also used in the lower grades, again, for the mathematical structure, and that's the important part of understanding algebraic thinking and reasoning. What is the structure? What are the tools that I need to be able to express my problem as a manipulative, the language, and then take it to the next step, the symbols.
And the other thing also, too, is that the representation of the algebra in the manipulatives and the representation of the symbol in the symbols is pretty much the same ideas. But what is common through both of those, whether you're using manipulatives or symbols, is the language. Many times in mathematics, when we have manipulatives and then we want to work them into symbols, we use one set of language with the manipulatives, and then we use our common language that we use in arithmetic with the symbols, and the kids don't make that connection. You need to have the language with the manipulatives and the language with the symbolism exactly the same, so all they're doing is taking they're going from one context, namely the models or the manipulatives, into another context, namely the symbols.
And the manipulatives are the beginning of the mathematical modeling that you get when you come up with the symbols, and we call those eventually equations.
And so after step D, we have our total. Now remember, the number that we chose was n. So if we used a number from a table of values, we would have gotten the total from that table of values. So if we had used 5, we would have gotten 26. If we had used 2, we would have gotten 14. In this case, we used n as our number, and when we worked through our number puzzle, we got a total of 4n plus 6. So this is the total, t, for the number n. And so this is the way we produce our formula, or the function, if you want to call it that, of t equals 4n plus 6. Now this is a function because I can put any number in for n and I'll get a value of t. It's also the idea that n and t are variables because I am not restricted by what numbers they can be, especially n. I can choose n for any value. So therefore, n in this case is a variable. A variable, just because you have a letter, does not mean it's a variable. If that letter already has a number attached to it, it's not a variable. So in this case, you have the function t equals 4n plus 6, and you have the variable n. And I think from this you can see that if introduced correctly, all this stuff, functions and variables, really can be done very nicely if in fact you give the students something to latch onto, like a number puzzle. So we've seen our number puzzle in three ways: as a table of values, where we have the common ratio; as a graph, where we have the pairs on a line; and now as an equation, where n stands for the number and where t stands for the total. Now, in writing the equation, by the way, you could take a step back here and not write t equals 4n plus 6. You could actually write the word total equals 4 times the number plus 6. And let students work with that until they really feel comfortable with it, and then begin to substitute the n for number and the t for total. In a sense, I don't think that'll take too long, because they will start saying to you, why do I have to write the number? Why do I have to write the word total? I would say to them in that case, okay, you can write the letter T for total and N for number, but every time you write T, you have to say total. And every time you write the word N, you have to say the word number. This keeps the ideas revolving around in their mind while they're writing the algebraic symbolism.
So as you can see, what we've done here is looking at the table of values, a graph, and an equation. So if you go back to one of the previous slides where I talked about what are the elements of algebraic thinking, one of the elements of algebraic thinking is looking for patterns and verbally representing them, and with tables or symbols, and looking to apply the relationship. So we're giving you a table of values by looking at an expression, or just looking at the table. We're looking at a graph, which can we explain what's happening here? Let's look at the ratio, why it's increasing or decreasing. As Frank stated before, if you look at your graph and you look at it and you want a number that's not a whole number, 3.5, can you justify why it came out to be 20? And looking at that relationship. So here again, we've given you three different ways of starting to look at that algebraic thinking.
So through the number puzzle, you could introduce students to algebraic thinking, leading them from the constructing of the table of values. They're starting with number. That's what they're strongest in. I don't say they know everything about it. Strongest is a relative word. They may not be strong in number, but that's where they're strongest. B, they go to a drawing of the graph, and then finally leading them to C, creating the equation. So to review all this, we started with a number puzzle, okay? So what we'd like you to do is try this number puzzle. Here's another one. You pick a number. Again, use the whole numbers from 2 to 5. Multiply it by 3. Give you time to multiply it by 3. I'm using my fingers myself. Add 1. And then multiply by 2. Now, if you take this number puzzle, which is different from the first one, and go through all of the steps that we did before, review this webinar, and go through the steps of writing the table of values, writing drawing the graph, and then coming up with the equation using models, you will see this will give you a different equation, but it will give you an algebraic equation nonetheless. And when you do, if you do this with children, what we would suggest you do is, in developing the table of values, have them put the blank table up on the smartboard or the board, and have them actually come up and fill in the values and see the way, and then have them talk about what patterns they see. So the instructions go from construct a table of values, to draw a graph, to create an equation. That's our theme.
So the final outcome would be that a strong foundation in proportional reasoning can support a student's understanding of linear functions and graphs, and in the form of y equals mx and y equals mx plus b, and in measurement situations. So if you're looking at what we've done, you're looking at coming up with a number puzzle that's leading to different parts of this algebraic thinking, looking at the table of values, looking at a graph, being able to go from the symbols or the words into the symbols, looking at the manipulatives, looking at what the rate of change is, that ratio, how it's increasing or decreasing. And eventually, when we looked at the graph, we saw that it was linear. Eventually, they're going to come up in algebra. Well, what does that linear model represent? So when you look at manipulatives, they are a model. When you look at the linear equation, that is a model. They're models in two different representations. One is using manipulatives, which is more visual, and one is using a little bit of the abstract. So as you come through all of this, you're looking at getting the students to go from the concrete to the abstract, looking at how I can move through those processes and getting them, especially the habits of mind, being able to do this with thinking and that flexibility and that fluency of moving through the process without having to really struggle to think about what they're doing. It becomes natural. So starting this and moving through the process prepares them for what eventually will be the more advanced math, the more abstract math. You know, algebra to many students is abstract because you're using letters and not numbers. So therefore, seeing this as they're moving along makes it a lot easier. It's a progression. And that's what the habits of mind are, a progression of going from the very basic to getting to the more advanced, the fluency of moving through this.
And it's very interesting that we have this slide, y equals mx plus b, that I think everybody remembers from somewhere in their background. And yet, that's exactly what we've done here, except we had an equation that said t equals 4x plus 6. And the same thing that happens with y equals mx plus b happens with t equals 4n plus 6, except what we have found is, and when teachers have used this with children, children tend to be more knowledgeable about what's going on with t equals 4n plus 6 than if they're just told about y equals mx plus b. And one last thing, if you're going to try to make up some of these number puzzles, or if you're going to have the children try, and that's really a treat sometimes, please have them use the models. Don't have them use paper and pencil, because they can make certain mistakes in the arithmetic that will lead them to places that would just be a problem for them and start to be confusing. Always have the models available. Always go through it with the models, and then from the model, do the table of values, do the graph, and then do the equation.
And for the younger ones, in making up the number puzzles and using the models, it's a nice way for you to see if they really have a handle on our arithmetic structure and what they can do if they're adding and subtracting and multiplying, dividing. What are the relationships, and being able to explain it. So again, using these models is a nice way of having you really get to understand what the students do and do not understand, especially through communication, that ability to communicate. A fun thing is to make up a puzzle and try to stump your partner. You know, what did I do? How did I get back to my answer? What were the properties? It's that mathematical structure that they have to understand before they can generalize. And the other thing is, yes, we're using y equals mx plus b and y equals mx, which are the standard notation, but using t is equal to 4n plus 6 also gets students to understand that not everything has to be an x and y. What does that 4 represent eventually? What does that 6 represent? And what did that t represent? So it's, again, notation, and students get stuck in one form of notation, which they shouldn't. It could be t equals 4n plus 6 or y equals mx plus b. So it's that moving them through along all of this, which is a nice progression to going from the very simple to the little bit more complex, and using the structure and the reasoning to get there. You know, the questions can get more involved as they move along. So we'd like to thank you. Are there any questions that you have for us? Because I'll pull it over, and if you have any questions, I would like to take some questions. you can put it in the chat so that if you have any questions about anything that we did this afternoon,